Hello, and now we'll start on lecture 15, and this is a very important lecture. We're going to discuss parameter estimation, how we come to understand the best value of the different parameters that a radar measures, and how we track targets that are moving. That is, how we correlate different detections one with another so that we understand that they all came from the same physical object. And they're all, as you would intuitively think, they're all part of a track. And this lecture 15 is going to be divided up into part 1, and lecture 16 will cover part 2 of this overall parameter estimation and tracking subject. Now, as we move on, here we've got our radar. We've been looking at it so many times you're probably blue in the face about it. And first we're going to discuss parameter estimation, and then later on in lecture 16 we'll be discussing tracking. Here are photographs of different radars that do tracking. Some radars perform multiple functions, like the Bemused radar, and what they'll do is perform a surveillance function, and then they'll track the different targets that they detect. And the same with the multiple object tracking radar, the MPQ-39, which performs at ranges. It's a scorekeeper. Tracking radars, when they're used in the range instrumentation mode, are scorekeepers, so to speak. There'll be an event go on. It might be a fighter plane launching a missile at another aircraft, and they'll track both fighter planes and the missile and take very accurate measurements on the encounter to see what happened. Or it might be a missile test, and they'll track very accurately to see when, in early missile tests during development, things go wrong with the missile, and these tracking radars will tell the people who are developing the missiles what went wrong a lot of the times by very, very precisely and accurately measuring the trajectory. And here is here are two instrumentation radars. The only difference between the FPS-16 and the MPQ-39 is that this is a lens array with exactly the same pretty much aperture and power, but because it's an array, it can track about 20 targets that are within the field of view of the array, whereas the FPS-16 is a single target tracker. So this can do the work of a lot of MPS-16s. And this is a classic, one of the first radars developed. It's still in use today, that do tracking at U.S. ranges. And here's the TradeX radar, a range instrumentation radar that's used at the missile, at the Reagan Test Center on Kwajalein to take measurements on missiles that are being tested, usually launched from Vandenberg Air Force Base. And here, of course, we have the FAA's airport surveillance radar, and it is known as a track while scan radar, in that as it rotates, it collects data, and in a surveillance sense, and then it correlates the data from scan to scan to track the data that comes in from scan to scan to form a track of the aircraft as it progresses across the airspace of the airport surveillance radar. And that airspace is about 60 nautical miles from the location of the radar. And as you can assume, these airport surveillance radars are located at the edges of airports. Now let's introduce the subject. Here we have a radar and its antenna beam and its side lobes pointing out at a target. And the radar will measure directly certain observables. It has the ability to measure range from the time delay, from the angle that's measured from measuring from the servos, the pointing angle of the antenna. It'll measure azimuth and elevation. If the radar is very well calibrated, it will measure the amplitude from which can be derived the radar cross-section. And if the range extent, the range accuracy is sufficiently small and the bandwidth sufficiently high, it can measure the radial extent of the object and the size, and it can measure the cross-range extent by doing inverse synthetic aperture processing on the target, which is a subject for later discussion. And it does that by using the radial velocity of the target, which can be measured using the Doppler effect. And from these observables that are in blue, we can derive the acceleration, the angular motion about the center of mass if it's a fixed body, and if we look at the trajectory as an object slows down in the atmosphere, we can measure the ballistic coefficient of the object. And so the quantities in blue are measured directly, but these other quantities of motion can be derived from the observed ones. Now let's just talk about what we mean by accuracy, precision, and resolution. First, let's define what we mean. Precision is the repeatability of a measurement. It doesn't necessarily mean that that's the true position, but a high precision measurement will always give you the same value with very little shift. Accuracy is the degree of conformity of the measurement to the true value. So accuracy tells you, are you really looking exactly where the object is that you want to measure? And the bias error is the true value minus the average measured value. In other words, you think the target's here, but it's over in another direction. There's a bias error. And these bias errors have to be calculated for range instrumentation radars and subtracted out so one can understand what the true value is. And here we have the two targets at one at 0 degrees and one at 6 degrees. And you can see that we can easily resolve the two targets. You can see that this one is heading up. These are side lobes. Goes down. It's resolved. And here we have targets at 0 and 3 degrees. And we can't resolve them because the beam width of the radar doesn't allow us that resolution. The targets are closer together than the resolution of the radar. And that brings us to the definition of resolution. It's the offset angle or range required for targets to be recognized as separated. Now this is a neat little visual example to show you the differences between accuracy and precision. Here we have in the middle, we obviously want to point towards the bullseye. The bullseye is truth. We have very high precision because say we're shooting a gun and we get holes in the target up in these 4 locations. We're very high precision in that they're all clustered together, but the accuracy is low. We're not hitting the bullseye. Here what we have is both low accuracy and low precision. They're not clustered as they would be here with high precision, and they're not high accuracy. When you have both high accuracy and high precision, they're clustered about the true value. So this will show you the difference between accuracy and precision, and a lot of people can make the difference. about that when they talk about it, but these are the definitions. And since we're talking about the accuracy and the precision of the different instruments, I want you to know exactly up front how they are defined. Now let's look about estimation. The four major observables that we measure: range, angle, Doppler, and the amplitude of the reflected echo from the target. First question we might ask is, for these different quantities, how accurately can we measure them? Now, after bias errors are taken into account, noise is the key limiting factor in the accuracy in measuring the above observables for a single measurement. And the exception in this angle measurement is where, for very low angle tracking, multipath errors, as I pointed out in the propagation lecture, where the part of the beam bounces off the ground if it's flat and can come up, and the phase of the main beam and its multipath path can interfere, and they can cause large errors. But these are conditions where you're looking at it at a fairly high, reasonably high elevation angle. And the theoretical RMS error in the measurement of, say, a range interval M, or an angle alpha of the beam, its theoretical form, where this is the accuracy, the error on M, the observable, is a constant that varies between 1/2 and 1 times the interval that you're trying to define, like it'd be the beam width. What fraction of a beam width can you measure? Or what fraction of a range cell, a Doppler velocity? And it's K times M, that measurement of the range cell, divided by the square root of the signal-to-noise ratio in natural units. Now let's look at the limitations on range estimation. Estimation of the range of a target is based upon using A to D sampling of the measurements of the round-trip delay time. So the delay time, we get a sample, and what we usually will get, we set up the measurements such that we sample the range at about the range accuracy, 1 over the bandwidth. And for time delay measurements, such as range, the value of K depends upon the shape of the radar's pulse spectrum and the pulse's rise time. For a rectangular pulse whose width is whose width is capital T, delta tau is equal to tau, the pulse width, divided by twice times the square root of the signal-to-noise ratio, which yields the error in measuring that range cell is C times T over 2 times the square root of the signal-to-noise ratio. And for a train of pulses, it just boils down to this equation, where T is the dwell time, and this is the pulse repetition frequency. Now let's look at the theoretical versus the practical accuracy limitations. For looking up the theoretical limitations on each pertinent observable, this is a very long lecture, and it's a very big chapter in Skolnick. And I'd like you to go to section 6.3 in Skolnick and read the derivations of the theoretical limits in both time, frequency, and angle. In range, it's going to depend on the signal-to-noise ratio, the pulse width and width, as I mentioned, the effective bandwidth, and the number of pulses. In Doppler frequency, it will depend on the signal-to-noise ratio, the pulse shape, and the integration time. And on angle, the signal-to-noise ratio, the type of measurement technique that's used, and you'll see when we measure angle and split the beam, so to speak, there are different ways to do that monopulse, conical scan techniques, and we'll go through all those in detail. The shape of the antenna pattern, that is the illumination distribution of the beam, the antenna size, and the frequency. So the error in our accuracy limitations will depend on these different properties for angle measurements. Now let's just look at angle measurements in general. And for each, if you're measuring an angle of arrival, and this is the true target location, and this is the probability density if you measured, say, 1,000,000 times the target location, you can see, I want to point out certain things. First of all, that this would be a biased estimate because it's clearly narrow, it's precise, but it's not accurate, and it isn't symmetric around the true target location. And in this case here, in blue, that's a biased estimator also, but in this case, it's due to multipath errors. Okay? Now, there are unbiased estimators, and one of them is signal-to-noise ratio. And we see here, with very high signal-to-noise ratio, remember in the accuracy, signal-to-noise ratio is in the bottom, so a high signal-to-noise ratio will give you a very narrow measurement, a very accurate measurement of the target location. And a low signal-to-noise ratio measurement will give you a poorer or broader probability density function for the angle of arrival. And of course, this sort of defines the different kinds of estimation issues that will come up and we'll be talking about. Now, when we look overall, big picture, and we really work hard on making a dish radar as accurately as possible, there are a lot of different errors that come into play. This view graph shows you the relative RMS angular tracking error versus the relative range. And this is in logarithmic scale, and so is this. Okay. And these are relative units. And you can see that there's going to be, in the antenna structure, there are a set of servo mechanisms that when the radar is a little off exactly on the location of the target, will sense an error message, you'll see, and will take you back. And will overshoot a little bit. And then back and forth and back and forth. And that's the servo noise, the noise in the servo mechanism, and that is constant as a function of range. The amplitude fluctuations of the target, whether it's a swirling target, 1 or 2 or 3 or whatever, they're a constant also. Now, there are two other issues that will come into play. One of them is the receiver noise and the type of mechanism we use to keep the beam pointed directly at the antenna. Okay? Now, the receiver, and also glint. Glint is when you have a complex target like an aircraft. Think of it just a two-engine aircraft, turboprop, commercial. There's going to be scatter off the engines, scatter off the wings, scatter off the fuselage, scatter off the elevators, and the different the back of the cockpit. The energy will go through the cockpit into the back of the seat and will reflect back. So there's going to be a lot of different scatterings that make up the whole electromagnetic return in the cross section, and they are going to change from scan to scan. And those amplitude fluctuations pretty much stay constant as a function of range. Okay. Now, receiver noise goes up with the square of the distance away. And the glint goes down the farther away you get because you're farther away from the Earth. So glint will take the error down, and receiver noise will take the error up. But then we've got, in this red and blue, the errors, when we've combined everything, this is the total error if we're using the monopulse technique to keep the target on beam, and I will explain later the monopulse technique in gory detail. And also, and this in red, is the receiver noise when for a conical scan, and the receiver noise for monopulse are slightly different, and so we get two different total errors for the conical scan and for the total error in the monopulse technique of bringing the antenna back to where the target is exactly. And if you work your total hardest, 1/10 of a milliradian is about what the best people can do. And let's again look over again, just summarize the sources of error or the signal to noise ratio, whether we were using monopulse or conical scan, the servo noise, and the amplitude fluctuations. And generally speaking, this is one of those rules of thumb I keep back here in my thinking cap, that the angular accuracy is pretty much 0.7 times the 3 dB beam width divided by the square root of the signal to noise ratio when you're out in this middle area. Okay. And of course we have the issue when we have when we're in very close, multipath will be a big source of error. But that, of course, would bring you up to way up here. Okay, now let's look at angular accuracy with a track-while scan radar and look at some actual data. This is sample output of data from an FAA radar, an airport surveillance radar. And here is these are range rings. We're looking at the southwest quadrant of the radar, and here's just the portion, an arc of the 20-mile range ring, and here's the 10-mile range ring. So this is good high signal to noise ratio. And you see here on 3 scans this track was detected. And these other tracks were detected quite solidly. And what we're going to do is look at this particular track that's detected. Okay? And let's look at just one of the measurements in that track. And this is what the detections will look like from one aircraft as it's seen by one beam width. And this particular radar detects the target, can detect it in multiple Doppler cells, up to 8. So here we see, and the size of the dot is the size of the detection. Whether the big dots give you an idea of the size. And so you can see that the target, this is all from one target, is seen in adjacent range cells twice. And here it's seen in both PRFs twice, but in this range cell it's only seen in one PRF. And in this coherent processing interval for both range cells. It's seen in both. So when we're calculating the range, you can take a weighted average of the range, weighted on the amplitude, to get the exact range that we'll put into this. And this is called consolidation and interpolation, is the process that's used. And we'll talk about that later when we go into tracking and in detail the tracking process. But this consolidation goes into giving you one of these dots. And so then what we did was took 100 tracks, like this one here, and we fit them with a polynomial looking at the RMS average error. And then we plot that error. And we see that the average error is 0.14 degrees. And the beam width is about a tenth of that. Excuse me. The beam width is about 10 times that average error. So you can see we can split the azimuth 10 to 1 in this range. Now, I want to go back and mention that when we consolidate these different detections, we average not only in range, but also in angle, and weight them to find the average angle of the target and to measure its average range. And also, we do a similar process with Doppler, which I'll explain later. Okay? Now, to make Doppler estimation, first what we do is, here's the Doppler frequency we measure, and the radial velocity is twice the Doppler frequency is twice the radial velocity divided by lambda. And the way we detect targets in a pulse Doppler radar is to set up a bank of filters. A filter bank spans the entire radar system, Doppler frequency band. And the detections are isolated within a given Doppler filter that pass threshold much of the time. We can use two closely spaced filters offset from the center frequency of the Doppler filter containing the detection. And Doppler estimation procedure is similar to angular estimation, with angle and frequency interchanged. So what we can do is see how close they are and what the amplitude is. And if one of them is bigger than the other, well, what you can simply do is just take the amplitude with one Doppler filter, the amplitude at another, and take a weighted average given the amplitudes, and that'll give you a better measurement of the Doppler frequency and also the radial velocity directly from the radar measurement. Now, to measure radar cross-section accurately, we come out of a radar, and eventually you measure A to D counts, which go from 0 to 1024, I think, for a 10-bit A to D converter. The measurement of the radar cross-section of the target in a test environment, we discussed that in detail in the lecture on radar cross-section. But what one wants to be able to do is to measure the RCS of a target on the fly. Literally, what I'm saying is, say we have a time when we're at a test range and we want to know exactly what the calibration constants within the radar are at that given moment, because different hardware and not the software, which is digital and stationary, but different microwave components that it would affect the pulse width and different things can affect the amplitudes during our measurement. The amplification in the power amplifier might be a little low today. And so what we want to do is before and after a test, we want to find out accurately. We want to convert A to D counts to real radar cross-section values. And there are two ways that you do it. One way is to launch a balloon with a sphere, which would be, its RCS is well known and independent of orientation, attached to a very lengthy tether. And so that you can put in one given range cell that sphere and not have the balloon interfering. And then you will measure the range of the balloon exactly, then go through the radar equation, and then you can correlate A to D counts to the exact ranges, and that will give you the exact transformation coefficients going from A to D counts to RCS. Now, if you're dealing with radars that are looking up into space, there are satellites up in space that are spheres, pretty exact spheres, and the calibration spheres, and people use them regularly. And what people will do with those powerful radars is measure the calibration sphere as it goes around before the test, and then the calibration sphere, whether it's airborne or in space, after the test, to make sure that the constants didn't change during the test. And so that's how radar cross-sections are accurately measured off of test ranges when this is an operational method, and the methods discussed in lecture 10 are ones that would be used the first time you want to know what the cross-section of the object is. Now, the calibration process, we're going to continue. The measurement's always performed in the far field, and a radiosonde is usually a balloon launch separately to measure the pressure, temperature, that is the index of refraction of the atmosphere as a function of height, so the propagation accounts can be, such as ducting and multipath, may be taken into account properly and accurately. And high-power radars, as I said, use satellite spheres that are satellites to perform the same function. And you also, because the atmosphere can change things, put up radiosondes to measure the properties of the atmosphere and the losses in the atmosphere accurately. And the RCS accuracy is usually limited by the ability to measure the atmospheric properties of losses as a function of the sphere's range and elevation angle. Because if you put the radiosonde up at one particular location, you're usually going to have a slant range to a satellite, and that could be tens of miles away or 100 miles away if you're measuring with a satellite, and consequently you're measuring the atmosphere where you are and not everywhere linearly along the path. So it's the atmospheric properties that are going to limit you in your ability. Okay, now let's look at single target tracking techniques. That's going to be the topic of the next lecture, and we're going to take a break here.